let's pick up where we did last time, which was we had this instruction set. So let me blow up the text a little bit so it's easier to read. And I need to make some edits to this, but mostly it's all there correctly. For our sort of toy little processor, what it's capable of doing. There are 12 instructions, and one of them is the halt instruction, so that we might even not want to count that one, because just stopping is not really doing much. So I want to kind of elaborate a little bit on, we'll go back through one of the programs we looked at last time, doctor it up a little bit, change it around, and then start to look at some more exotic kind of things. So two things I want to sort of say about that is the author of the book who made up this this processor, okay, did so a very, very long time ago, and he's now a retired, so his career, right? He's been through a 40-year career. When he made this up, he was doing so kind of inspired in some sense by computers of the 70s and 80s, okay, these simple 8-bit processors, but also wanted to gloriously simplify it from one of the real ones for practical teaching use, okay? So this single page, and I need to actually kind of make 2 copies of this, and I'll explain why later, is essentially the entire instruction set for this processor. For a real processor, even one of the 70s and 80s, this would be many pages to flesh out how it all works, okay? Up to and including a modern processor. So for example, the ARM processor that's inside the Raspberry Pi up here on my workstation, and in basically every iPhone and Mac, or iPhone and iPad that's out there, and some of the newer Macs. So does anybody have one of the new MacBook Airs, like that's got an M1 or M2 in it? M1, yeah, those are actually ARM architecture, okay? So to fully understand that architecture, you have the several thousand page manuals, okay, that ARM produces. There's the Programmer's Reference Manual and some other ones, right? Now, how many people really love the idea of digging through several thousand page manuals, right? Not everybody that, say, works at Apple needs those. The people in the hardware group or the operating system group do, but the people that are designing their store on the website and doing the product photos and stuff, they don't need that, okay? Right. Okay, so when he designed it, so there's 2 things about the book. Let me take a flashback for a moment. We talked about floating point, right? And I showed you guys this 8-bit floating point scheme. And it seemed a little weird at first, particularly that hidden 1, right? So what was the hidden 1 again? Let's remind ourselves. But you don't actually have to store it, right? So in scientific notation, right, what was our convention? You always have exactly 1 digit before the decimal point, right? 6 point something times 10 to the something. Well, in binary, you don't put a 0. So what's the only other option? A 1, okay? And so you have 1 point something times 2 to the something. Because that 1 can't be a 0, we don't need to encode it and spend a bit on it because it's assumed. That's the hidden 1, okay? So Brookshire, the name of the author, he in his book, in the floating point section in whatever chapter it is, okay, he did not do the hidden 1. Okay, you gonna live over there?
Don't know.
No? Am I that funny, or you just need to go get some water?
Couldn't tell you.
Oh.
Just started.
Oh. My fly's not down or something, is it? No?
I'll just say
No?
you're that
Okay,
funny.
it's up. I'm that funny?
Yeah.
Okay, great. Okay, so where was I before I was so rudely interrupted? the hidden one, right? So he defines the floating point standard not having the hidden one. Okay, so when I first taught that, I was like, okay, right, fine, whatever. And then flash forward a couple of years, and I'm teaching an advanced CS class, and where we're looking at 32 and 64-bit encodings, and they do have the hidden one. And I'm like, wait a minute, what's going on here? And then I realized that I'd done the worst possible thing I ever could, which is I taught 8-bit floating point not with the hidden one, and then had students who needed to do 32-bit with the hidden one because that's how it actually works. So I threw out his part of the book and rewrote all those floating point notes to include the hidden one. Yeah. Okay, and that's what I'm teaching you guys. So those of you who go on to say CS241 would be next fall would be an appropriate time for you to take it if you so choose. On machine organization is going to be a semester all about what we're talking about in this week and part of next week. Okay, um, and uh, so I want the floating point that you guys learn now to scale up to the floating point of that you'll see in the future, or real floating point, if we call it that, right? Because nobody does 8-bit floating point. The only reason we did it was it's much more convenient, less to write down. Okay. Okay. So Brookshire original architecture has an operation. It actually had two operations for add, operation number 5 and operation number 6. Operation number 6 was addition of floating point numbers. Okay. But again, he assumed he did not have the hidden one. Okay, so I thought that was kind of silly. So I've redefined the processor to not have any floating point capability whatsoever. And that left me with opcode number 6 unused. Well, his original vanilla version did not have subtraction. So I'm like, okay, we've got addition, let's go ahead and have subtraction. Okay, so I'm redefining opcode 6 to be subtraction. But, here's the big but, about which I cannot lie. Okay, come on, that was funny. No? You guys get the joke? Okay, just making sure. This simulator, okay, that was written by this guy named Joel, very nice guy. I've not met him, but we've corresponded through email. He basically programmed and set up this simulator as a class project when he was in I think, graduate school. Okay, I found it at some point, and I've been using it ever since when I'm teaching this part of the course. Super handy to be able to put code in and actually see it executing. Okay. Now, when he programmed this, though, he programmed it for the vanilla architecture from the book, which had floating point and no subtraction. Okay. Which means if we want to simulate our code, we can't use the subtraction operation because it doesn't exist in vanilla Brookshire. Okay, now, the two students I think I mentioned last time, so how many of you guys know either Owen Runge or John Barker? Yeah? They worked with me over the summer, and our project was to build our own simulator that did incorporate these new operations and also gave us the ability to do some extra stuff. Okay, we're not done yet. Okay, so this is still very much a work in progress. So the process of you guys turning code into the numbers, the sequence of operation codes and stuff, for right now is still manual. Okay, and that's probably a good thing for right now that it's still manual, but for a really big program, you wouldn't want it to be manual. Okay, so with those caveats in mind, we're going to look at two programs today, and then we'll start to talk about, okay, let's pretend we did not have subtraction as an actual operation. How would we do subtraction without it? And I claim that not having the subtraction operation doesn't prevent us from doing subtraction. It just means we have to go through a bit more rigmarole to do it. Okay, so does that kind of make sense? Big picture where we're going? No, you guys are just all craving chicken tenders. Yeah. Are any of you capable of speaking today? All right. Okay, so let's go back to one of the programs we looked at, or the program we looked at last time. Okay, and it was here. So first we wrote it in English. Okay, let's say that I want to add the number 1 and 2. Not shockingly, the answer is 3. But how would I actually do that with this processor? Well, the instructions are load one register with the number 1, load another register with the number 2, add them and put the answer in someplace, store that answer out in a memory someplace, and then halt. Right? So the simple act of adding two things required really 5 steps. Loading the two numbers into registers where we can work with them, actually doing the addition, and then storing our answer someplace for posterity's sake. Okay? Okay, so you guys would certainly agree that this set of instructions in English is pretty clear. Yeah? Okay. One other note that I want to make here is you guys see how I have hashtags in front of some numbers and dollar signs in front of others? Okay. That's a convention that I made up, partly inspired by other languages, similar languages, in order to make the following distinction. Okay. If I tell you a number like FF, that could mean two things. It could mean the memory address FF. Okay, so like the number on the front of the mailbox. Here is mailbox FF. Or it could mean an actual number FF, which is, what is FF, by the way, is a signed integer and an unsigned integer. You guys should have this one memorized. It's all ones in binary. Okay, so what's the value of that? As an unsigned integer, it's 255, and as a signed integer, it's -1. Okay, and I'll prove why later. Okay, no chicken tenders for you. Why? You're in a frat? Oh, you don't like them anyway? Oh, fine. You're going to be the like picky child eater where it's like, but you love pizza. And then suddenly today you hate pizza. Yeah. Okay. Okay. So the difference here is anytime I'm talking about a specific value, a specific number, I'll put a hashtag in front of it. And anytime I'm talking about a memory address, I'll put a $sign in front of it. Okay. Seems like a reasonable thing. That way, once we know that, you can never get numbers and memory addresses mixed up because they have different symbols in front. Okay. And now, why did I pick the hash mark and the $sign? Again, I was trying to mimic real assembly languages for real processors. Okay, that was sort of the inspiration for it. Okay, so what instruction do I need to do to load a number into a register? Okay, well, what's the name of that instruction? Or in my table, I called it a mnemonic. Let me scroll back up to that word because it's one that's you have to practice saying out loud. Okay, mnemonic. Let's all say it together. Mnemonic. Yeah. Okay, it's one of these fun double consonant Greek roots like pneumatic or asthma. No, no, a double consonant. Yeah. Okay. Anyway, or pterodactyl. That one's fun. Okay. So, what does mnemonic mean, by the way? Well, if we don't know, what do we do? If only we had Google. Or, hey Siri, what does the word mnemonic mean?
As a noun, mnemonic means a device such as a pattern of letters, ideas, or associations that assists in remembering something. Do you want to hear the remaining one?
No. Okay, so something designed for aid of memory. Okay, so aid of memory, right, or mnemonic here means sort of a code for which operation we're doing. Okay, so it's a three-letter sequence that stands for the full-blown operation. Okay, and we've got LDR is this mnemonic that we're working with for loading a register with a specific value. Okay, and it happened to be opcode number 2. Okay, so I'm going to load which register with which number. Register 1, say, with the number 1. Okay, and then what? Load register 2 with 2, then do the addition. Okay, and the syntax here, syntax means how you actually write stuff. Semantics means what it means. Okay, so the syntax is, notice the order. I'm adding which two registers together? 1 and 2, and where am I putting the answer? Register 3. But I actually list register 3 first. Does that feel maybe a little backwards? Okay. Tufsky Shitsky. Okay. In the sense that, like, I mean, Brookshire made it up to be in that order, right? We could redefine it, sure, but this actually matches some real languages out there. A lot of times you put the destination first, not last, right? But you have to know that table to understand that, right? So think about the table actually, well, as a dictionary, right? So if you see a word, like let's say you're in a Spanish or French or something class, right? And you come across a word. So who's in a Spanish or French class or something? Okay. What's a word that you had to look up recently that you didn't know what it meant? Aquí, behold. Okay. Aquí. I'll have to trust you on that because mi español es muy malo. Okay. All right. So you looked it up and you saw the meaning and now you remember it. Better question. How many times have you looked that phrase up?
Once.
Just once? That's impressive. Okay. But how many of you guys, when you were in some sort of language class, you found yourself looking up the same word like 16 times? Yep. Yeah, okay, we've had that experience. All right. Eventually what happens? Yeah, if you've looked it up 16 times, by that point, damn it, you probably are going to just start to have it memorized by osmosis. And that's going to be the same thing for our table of opcodes, is that eventually it's just going to stick into your head. Now, I'm not expecting you guys to memorize it because, well, for two reasons. One, like if I want you to memorize something, I want it to be worth memorizing. You don't need to memorize that, but you're going to effectively end up with a lot of it by osmosis. Okay, the other reason is because when I was in school, I sucked at memorizing things just for the sake of memorizing them. And there were plenty of classes and stuff where I had to memorize a whole bunch of useless crap for no good reason other than to memorize it and be able to dump it on a test. And do I remember any of that now anymore? Not hardly any of it. Okay. Um, Maybe the two things that I can't tell you the dates of lots of stuff, but I can remember, let's see, um, what are the verbs to be? Or the being verbs? No, in English. And it's not just to be and is, right? But is, are, was, were, uh, is, are, was, were, uh, been, being, being, appear, become, seen, look, smell, feel, taste, sound, remain, stay, turn, grow. I had to memorize that in 7th grade English. Okay, that's when's been useful when you're learning other languages. And then the other would be the opening of Caesar's Gallic Wars in Latin, which is, Gallia est omnis divisa and partes tres, and so on. Okay. All right. But I'm not going to make you guys memorize crap just for the sake of memorizing it. That's stupid. It's not a good use of your brain power. But I think what you'll find is that you'll mostly have that table memorized just because you're going to have to keep looking back at it over and over, and eventually it's just going to stick. Okay. Okay. So how do I know then that the order has to be that order? Well, by knowing the table. Okay, and reading the table. Okay, so I load two numbers, I add them, I store it out into memory, and then I halt. Okay, great. This is the assembly code, right? Still pretty human readable, but not that far away from the actual machine code. Yes? Okay, so how do I translate the assembly code from here to the machine code that's down below? Well, again, I need to look at the table. So how do I know that loading a register with a specific number is operation code number 2? Yeah, the table. Okay, and how do I know why I put the number 1 here? Well, what does this one signify? Which register it's going into, and then the O1 is the specific number I'm loading. Okay, so bam, that instruction's done. Check. Next one, well, the pattern holds, right? Opcode, which one? 2. Register, number, 2. Okay, it's all 2s in this case, but doesn't have to be. And then the addition one. Operation 5 is addition. What are my 2 source registers? Registers number 1 and 2. And what's my destination? 3. Right? So how do I know what order and what numbers to put where and all of that? The table. Okay. But would you guys agree that being able to write it first in this sort of quasi, like, this looks like computer code, but it's pretty easy to look at one of these instructions and with a copy of the table, turn it into the appropriate actual set of numbers. Yeah, would you guys agree? Okay, so that's the process of, quote, assembling it, is going from the assembly instructions to actual machine instructions. Okay, and right now, there's no automated way to do it for this language. For real languages, there are. Okay, those programs are called assemblers. And John's assembler is mostly working. We're not quite there yet. Okay, so eventually, what I'd like to have, and maybe by next week, we'll see, we'll have a thing where you could type in this, hit a button, and bam, it would spit out that. Wouldn't that be really handy? But for now, you suckers have to do it by hand, because back in my day, right, that's how we did it when we walked uphill both ways in the snow to school. Okay, good. Okay, so let's change the program around. And in particular, let me load it, okay, here with the hyperlink. And the nice thing about the hyperlink is it has the program already loaded into memory. That's part of the URL. It's actually very much like the Turing machine simulator. All you have to do is give me that link, right? And that will take me exactly to it, and I can do everything I want with it. Okay, great. So this is right now adding the number 1 and 2. Nothing particularly exciting about that, and there's nothing particularly special about 1 and 2 either. What would I do if I wanted to change the numbers here and add, well, give me 2 other numbers. 3 and 5. Okay, great. I want to add 3 and 5. Not surprisingly, I'll get 8, I would hope. Okay, so what do I have to do to add 3 and 5 instead of to add 1 and 2? What do I have to change? I have to change the O1 to say O3 and the O2 to say O5. Right? I have to change the program itself. Okay, do you guys agree that that will do the job? Yes or no? Okay, well, let's make sure and let's run it. So I put it in automatic mode so it will just step through automatically. And there we go. We got the number 8. Big shock. Okay, but I had to change the program itself in order to do that. Not always do you want to do that, okay? If I were to write a program that said, like in Python, that asked a user to type 2 numbers and then added them together and printed the result, the user would be able to type different numbers, but the program would be the same. Yeah? Okay, now I don't have a keyboard for this computer or any other kind of input device, but what I do have is a big pile of memory. So let's change this program so that instead of having the numbers hard-coded, it loads them out of memory, adds them, and puts the result in a certain spot in memory. Then I'm not changing the program, I'm just changing what data the program works with. Okay, so do you guys see the distinction? Right, it's not always to be avoided, but modifying a program is not necessarily always what you want to do. Okay, now, so technically, did I just modify this program? Yeah. Okay, now I didn't modify it in any dramatically complex way. I just changed a couple of numbers. But if I were really sloppy about that, I could really, really mess up my program. Okay. Now, have we actually seen something where somebody changes a program by editing numbers in hexadecimal? Have we talked about that before, other than just now? Well, when we watched the clip from The Martian, right? What was the clip from The Martian that we watched? Yeah, he figures out how to communicate with NASA, right? And how does he do it? ASCII table, okay? But then what else did he have in order to pull this off, Liam? Yeah, and it was those two pieces, right? He went out and dug up the old Mars rover that had the camera that could point in whatever direction, okay? And then he set up the sticks around it in a circle that had 0 through F, right? The hexadecimal characters. And between the two of them, NASA could rotate the head of the camera, and he put the little stick on it so he could see which one it was pointing at, okay, and see, oh, it's pointing at the A, and then it's pointing at the 2. Okay, A2, what is that in ASCII? 3, 7, right, and so on. And then he's able to decode their messages, and then he can, of course, write responses on the little whiteboard, and they can take a picture of it and see his responses much more quickly than ASCII encoding. Okay, so we saw that, right? Really interesting part of the movie. Hopefully, I mean, you guys have all seen the whole movie. Has anybody not seen the whole movie? Oh man, you're so missing out. It's a great movie. Not that there's anything going on this weekend, but um, maybe over Thanksgiving, watch it. It's a good movie. Okay. Okay. So that said, the oh, this is interesting. I think something's messed up with my capturing because it's not capturing. Oh no, there it goes. Okay. It's just laggy on here for some reason. Okay, so where was I? The Martian, right? But there's more to what he does there because eventually they send him a message that says, "Hey, go into the rover, the little truck he can drive around, and change certain values in the memory, and then the probe can talk directly to his rover, and he can use his keyboard and screen rather than having to do the thing with the sticks." Right? And that works much faster. But what is he doing? He's going into memory and modifying the program. Right? That was sort of a lesser part of that scene or collection of scenes, but it was a pretty important part to the movie. Yeah? Okay. All right, so we essentially just did that. Okay, so let's go back to the notes here and let's look at a slightly different version of the program. Okay, namely this one. Okay, instead of picking two numbers at from the get-go, let me say, all right, whatever the two numbers are, I'm going to pull them out of memory addresses FD and FE. So if I want this thing to add those two numbers up, I need to put the numbers 3 and 5 or whatever other values in those two memory addresses. Okay, is there anything special about memory address FD and FE other than they're right before FF? Nothing in particularly special. I just picked something. Okay. I've got 256 bytes to work with. I just picked the 3 at the very end. It's got to go someplace. Okay. Okay, so I'm going to load register 1 not with the specific number FD, but with whatever is in mailbox FD. Okay, so remember, or let's remind ourselves, what is the difference between the $ and the hash mark? Yeah, so what the $ is saying, I want you to go to that memory address and get something or put something there. Okay, so which memory address is the first instruction due or access? Okay, what number is in memory address FD? Do we know right now? Could be anything. It could be a boat. Okay, come on, that was a good Family Guy reference, right? You know, when they win a prize or whatever, and he's like, "Well, you can win the boat, or you can have what's in the mystery box." And Peter's like, "Well, we'll take the box." And Lois is like, "Peter," and it's like, "What, Lois? There could be anything in the box. It could be a boat." And so he takes the box and gets nothing, and then all of his friends, Quagmire and everybody, are driving these giant boats down the street. Yeah? No? Okay. No, I can't. I'm not going to right now. But okay. So I don't know what is in that memory address at the moment. I can put whatever number I want there and then tell the computer to run. Okay. So the memory address FD could have any of 256 different values within it. Maybe FD is in that mailbox. I don't know. Maybe it's 5. Maybe it's 8. Maybe it's a boat. Similarly, what's the next instruction? Yeah, same thing, except the destination register is number 2 this time, and it's coming from FE, different memory address. Okay? And then the addition instruction is exactly the same as it was before, and so for that matter is the store instruction. Okay, they're precisely the same as what they were before. Okay, so let's look at how this translated to the machine code. The last 3 instructions are identical, but what about the first 2? What's different about them from what they were before? Yeah, the values are different, okay, but also the opcodes are different. What's the opcode for both of those first instructions? Opcode number 1, which moves from memory to a register rather than a specific number to a register. Okay, so we see the distinction. Oui, no. Okay, and then FD and FE because those were the mailbox addresses that I wanted to look at. So how do I know to change the 2s to 1s? How do I know it's opcode 1 this time instead of opcode 2? Knowing, well, the $ told me it needed to be different, but how did I know it was going to be a 1? Looking at the table, okay, the instruction sheet or the instruction set back at the beginning. Okay, is that okay? All right, so again, we'd have to go back to the instruction listing to know which one goes with which. Okay, so you guys buy that? Okay, so let's make sure that this program works and see how it works. Okay, so I've got here, well, the number 1 and 2, I went ahead and put into memory cells FD and FE respectively. Okay, so what should this program do? Load those into registers, add them, and stick the sum back out into memory. Okay, so let's make sure it works. I think last time I used the step thing where it did it one step at a time, but if you hit clear and run, it will automate it and do half a second per step, which is fast enough to get something done, but still slow enough that you can watch each step happening. Okay, Good? Oui or no? All right, so did we get the number 3 in the correct memory address? Yeah, okay. Let's change the numbers to, what was it, 5 and 3 was what you guys picked earlier? Okay, and so what's in memory cell FF at this moment? Oh, 3, but after I run the program, what's going to end up there? Should be 08, right, the sum. Okay, so let's do that. And sure enough, we get 8. Hooray, addition works. Okay, so does that kind of make sense? Yeah? All right, so we're going to, well, both of these programs were relatively simple. They were just 5 instructions. They weren't doing anything particularly exotic. We're going to spice up, right? So right now, we're at like the honey barbecue stage of the wings. And then we want to get to like the hot barbecue, and then the Nashville hot, and then the mango habanero, and then the blazing wings. Okay. Yeah, you're okay with honey barbecue? Now we're going to get you guys up to the blazing challenge. Okay, so to start to ramp this up a little bit, I want to convince you that we can do subtraction without actually doing subtraction. Okay? And in order to demonstrate the idea here, let me go to the iPad, which now actually works again. Spoke too soon. It worked fine in the last class. Yeah, maybe it does hate this class. I don't know. Okay, so let's plug it in. This is really peculiar. iPad. And it's, go back to the home menu. Let's try plugging in it again. This is really peculiar, guys. Okay, well, plan B. All right, so let me write a number. Okay, so this is the number 1, right? 7 zeros and a 1 in binary. Let's suppose that I wanted to do the following. Well, let me do it this way. Okay, what's the answer? Right? So what have I effectively done here? I've done 5 minus 1 is 4. Okay? All right, and we know how to do the subtraction. We can do it with the Turing machine. We can, like, we understand how to do this. Okay? What I want to convince you is that we don't actually have to have subtraction or the ability to do subtraction to still get this result. Okay? So here, let me think of my number A as being 5 and B as being 1. And I just computed A minus B. Yes? Okay. Here's how I'm going to be sneaky. I'm not going to compute A minus B. What I'm going to compute is A plus negative B. Right? So what is negative B? Well, how did we do this when we were doing the 2's complement stuff? I know what B is. B is that. Right? So look, this is B. So how do I get the negative of that number? How do I get the value negative 1? What was our procedure? Huh? Flip the bits and add 1. Okay, so are we able to add 1 with our processor? Yeah, definitely. That's no big deal. The flipping the bits part, though, how do I flip bits with one of those 12 instructions that I have at my disposal? Okay, let me put up the instruction list again, and let's stare at it, and maybe you guys will figure out which of the ones will do the job. Nope. Okay, so we've only got 12 options. Really, it's only 11, and we can eliminate all the loading and storing and moving ones. We already know that it's not just going to be add by itself. We know there's no subtraction, and so what's left? These 4. Well, let's think about these. Okay, why do we have 2 different versions of OR here? What's the difference? Huh? No, it's I or for. Okay, what was our example of the 2 different meanings of the word or in the English language? Okay, but not both, right? So, would you like pie, or would you like cheesecake or creme brulee for dessert? Huh? Okay, so if you say both, you probably are going to get neither, right? You go out to dinner with your mom, and she says, "Oh, let's get dessert, honey," and because that's how all of your moms sound, I'm sure, right? And you try to get both cheesecake and creme brulee for yourself. Your mom's probably going to walk out and make you do the dishes to pay for the bill. Yeah? Okay. So that doesn't going to work. So that meaning of the word or is the exclusive case, or XOR is our mnemonic for it. Okay, great. The inclusive case is where you do permit both to be true. Okay, so if I asked, like, are you in calculus or computer science, some of you could totally say yes to that, right? You're in both classes. Perfectly reasonable. Dessert, not perfectly reasonable. Okay, so we have these 2 different ideas of or. Okay, one of them is going to be the one that we need. Okay, so what is the truth table for exclusive or? Let me write it up on the chalkboard over here, since my freaking iPad is deciding to mutiny. Okay, so for XOR, what's 0 XOR 0? What's 0 XOR 1? 1. What's 1 XOR 0? What's 1 XOR 1? No dessert for you, you get to do the dishes. Okay, that's why that one's the 0. Okay, so if I claim that the use of the exclusive OR is the trick that we need. But that's not enough by itself, okay? Because for me to use exclusive OR, I need 2 numbers. Well, right now, how many numbers do I have in front of me? Well, yes, but for this right here, when I'm just going to work with B right now, I only have 1 number there, okay? And I need to turn all the zeros into ones and all the ones into zeros. And I claim we'll use the XOR operation to do it, but I need a second number. Okay? 255. Okay? And it turns out this is the number that you want. Okay, so what does it mean to XOR 2 big numbers like that, or 2 binary numbers? Well, how would we do addition, for example? You do it one thing at a time, and then you deal with carries. And sorry, I'll finish here in just a second. That's my note to leave some time for the last part of what I need to tell you. Okay, so we know how you do addition, right? You do it 1 bit at a time. Well, similarly, how do you exclusively OR two numbers? You just do it bit by bit. So what is 1 XOR 1? 0, and all the other ones are 1s. And so I get the flipped version, right? So there's really two pieces to this. Using exclusive OR and this bit pattern of all ones, I can flip everything to zeros, or flip all the bits. If I can do that, and I can also add 1, then I have all the components I need to do subtraction. Okay, so we'll look at putting all the pieces together next time. Okay, now the last thing is, like, if I wanted to build a processor to actually do this, I need to be able to XOR 2 bits together. Well, actually, I need to be able to XOR 8 bits with 8 other bits. So I need 8 exclusive OR gates. Well, if only a certain computer science class, a bunch of different groups individually built one exclusive OR gate. If you can do it once, can you do it 8 times? Yeah. So I just need 8 of those circuits you guys built, and then I can do exclusive OR with 8 bits. Brilliant. Yeah? Okay. So like I said, first thing Friday, we'll look at how to put these pieces together and actually program it. Okay. I'm going to quit the stream here, but don't you dare move.